This lecture is Introduction to Rheological Concepts for Polymer Rheology and Processing. The first thing we need to discuss is the fact that rheology is not a basic subject. It is a very interdisciplinary subject, and it can be very difficult to understand. Traditional scientists need to move away from their expertise to understand some engineering concepts, and engineers also need to kind of step in and understand how chemistry, physical chemistry, relates to the materials they're looking at. For mathematicians, an understanding of physical chemistry is necessary, and other aspects related to microrheological studies like interfacial dynamics and things like that. For the non-mathematicians among us, a knowledge of non-trivial mathematics is necessary. Functional analysis is something that is part of rheology, and so is general tensor analysis. The general aim of this introductory lecture is to explain any rheological concepts to the uninitiated. Rheometry is the measurement of rheological behavior. Materials are generally investigated in simple flows. So these are steady, simple shearing flow, small amplitude oscillatory shear flow, and extensional flow. And the application of these simple flows allows us to kind of avoid some of the mathematical difficulties while still understanding and observing the full rheological behavior. The motivation behind rheometry is often that the observed behavior in industrial situations is correlated to an easily measured rheological function. Rheology is important to quality control and process control in an industrial setting. And rheology is really useful in assessing usefulness of a proposed model for a test material. And indirectly, rheometry is relevant in industrial process modeling as well. Understanding the rheological behavior of your material gives you more control over your process. In the previous lecture, we talked about the modern view of rheology, and that the extremes, in other words, classical elastic theory as determined by Hooke's law for solids, and Newtonian fluid mechanics as defined by the Navier-Stokes equation for fluids, kind of fall outside the modern view of rheology. And rheology seeks to study materials that fall in between, or the viscoelastic materials. So that would be Weber's silk thread, a viscous solid, or Maxwell's gases, elastic fluids. There are two important considerations to keep in mind as we move forward. First, intramolecular forces in the material we're looking at control how the material we're examining behaves. In other words, chemical nature controls physical response. Second, the time scale of our measurements or our observations are very important. Different physical responses can be observed at different time scales for the same material. So you have to bring the two together. So rheology seeks to understand the material structure from forces and timescales for changes, and microstructural motion from thermal or mechanical energy's effect on the molecules themselves. So first, we're going to define a few terms. The definition of stress is stress equals force divided by area, or sigma equals F over A. So some examples of stress. Pressure is a bulk compressive stress. A weight on a wire is an extensional stress, and if you slide a piece of paper over a sticky or gummed surface, that's a shear stress. And shear stress is what most rheological instruments actually measure, and the units of stress in this case are pascals. Defining strain. When a stress is applied, a deformation or a strain results. And for the purpose of measurement, we define strain as the relative deformation or deformation per unit of original length. So eta equals L minus L0 divided by L0. And L0 is the length after deformation, where L0 is the original length. So in order to understand viscoelastic behavior, we need to first understand the extremes. And so we're going to talk about solids and fluids. So first, discussing solids. Classical solid behavior is when a stress or a force is applied to the surface and results in an instantaneous deformation. And once that deformed state is reached, there's no further movement, no further strain. The deformed state persists as long as that force is applied, and this is considered traditional elastic behavior, things governed by Hooke's law. So here we have an example. The elastic modulus is constant at small stresses and strains, and stress is directly proportional to strain, producing a linear relationship, as you see here. So here is our stress versus our strain, and this is our linear relationship. And this is not a traditional looking spring, but a downward force is applied and there's a displacement. This is kind of your traditional spring. We saw this before in our previous lecture. Hooke's law states that the power of any spring is in the same proportion to the tension thereof. In other words, if you double the tension, you double the extension. So Hooke's law is the force on the spring equals the negative spring constant K times x, where x is the displacement. So here we have a displacement x with a force F. So you need twice as much force to get twice as much displacement. This is an example of stress and strain with no rotation. Shear strain is produced by the application of a shear stress. One of the diagonals is shortening while the other one lengthens. And it's only in one direction. And this is similar to what we see for a Hookean solid. So a shear stress is applied to the surface and it results in an instantaneous deformation. Once the deformed state is reached, there's no further movement. The deformed state persists as long as the stress is applied, and the relationship between these two is in proportion. So the stress equals the rigidity modulus times the strain. Previously we looked at one axis, just pushing on one side. Really, you have to consider all of the axes. Strain is made up of 3 orthogonal elements that can be further divided into components, and these line up with the x, y, and z axes. If we apply a simple strain, gamma, in our rheometer, this is made of 2 equal components, gamma xy and gamma yx. And when you restrict to simple and well-defined deformations, you can avoid a lot of the mathematical difficulty and still observe the rheological phenomena. You do have to pay attention to the tensor framework. Stress, again, is force per unit area, sigma equals F over A. Oftentimes this is presented as a scalar, and a scalar is a quantity having magnitude and not direction. But you do have to consider a more sophisticated network of tensors and to understand rheological concepts. And a tensor is a mathematical object that's analogous to a vector. It's a little more general though. A vector though is having quantity as well as direction, especially determining the position of one point in space relative to another. Now we're going to look at classic liquid behavior or fluid behavior. Typically we're looking at liquids, but when we're talking about fluids, we're not just talking about traditional liquids, we're also talking about gases, but typically the systems we're going to look at are actually liquids. So in a typically liquid system, motion is produced by the application of a stress, and the motion continues until the stress is removed. A constant stress will produce a constant velocity or a linear relationship, and this is considered viscous behavior. So this is also from our introductory historical perspectives lecture. So here you have 2 plates of area A, a distance d apart, and in between them is a liquid. A force F is applied in each direction. Sigma denotes the force per unit area, F over A, required to produce motion or shear stress. Sigma is proportional to the velocity gradient, or shear rate, U over D. Eta is the coefficient of viscosity, or in other words, viscosity from this point forward. And if you double the force, you double the velocity gradient. So you get this linear relationship. Sigma equals viscosity times U over D, the velocity gradient, or sigma equals eta times the shear rate. This is the relationship for Newtonian liquids, and glycerol and water are common liquids that obey this relationship. For linearity in rheology, these 2 relationships are describing elastic and viscous behavior. For Hookean solid, we're looking at the elastic behavior. For Newtonian fluid, we're looking at Newtonian behavior, but there's a shear stress related by a constant to a shear rate, and these are direct proportionality. Any viscoelastic behavior that we've considered thus far is also linear, and this linear framework proportionality can accommodate a wide range of rheological behavior. However, non-linearity is also very important to understand, and that's where we're moving by defining these solids and fluids. The framework of linearity can be very restrictive. Material properties change with applied stress. In other words, the rigidity modulus or viscosity can change with the applied stress. And the range of stress where materials behave linearly is limited. The applied stress need not be high to see nonlinear behavior, and this change can occur instantaneously or it can occur over time. And these can increase or decrease the material parameter of modulus or viscosity. Some examples of these are shear thinning. This is a reduction in viscosity with increased shear rate and steady flow. If you're talking about time independent, you're talking about pseudoplastic behavior. If you're talking about time dependent, that's thixotropic behavior. Time independent pseudoplastic behavior, one example of that is toothpaste. It sits on top of the toothbrush bristles without moving, but it can be easily squeezed from the tube, and that change in viscosity occurs almost instantly. Time-dependent shear thinning, followed by recovery, is thixotropic behavior, and one example of this is non-drip paint. This is time-dependent. The shear thinning does not occur instantaneously. It occurs as you spread the paint up the wall. And the painter doesn't really notice the increase in viscosity after you remove the stress, but you notice the result. In other words, you don't get paint dripping down the wall. And it stays on the wall while still wet. Shear thinning is just one manifestation of nonlinearity. There are many. And to understand rheology, you must understand the importance of nonlinearity. Here's an example of multiple different nonlinear fluids. All of these are time independent. So this is shear stress versus a strain, in this case shear rate. And there's a linear relationship for Newtonian fluids between shear stress and shear rate. For a pseudoplastic or shear thinning material, you have this sort of behavior. In the case of a Bingham solid, you have a initial shear stress that must be overcome, and then it behaves linearly. For a Herschel-Buckley fluid, you have an initial shear stress and that behaves pseudoplastically. One interesting material is a dilatant fluid, where you have shear thickening behavior. And this is the viscosity getting thicker as the shear rate increases. And we're going to do an activity where we mix starch with water to be able to see how this behaves. Here we have shear rate versus shear stress for nonlinear fluids that are time dependent, and these two are shown here are thixotropic fluids and rheopectic fluids. These demonstrate a time-dependent decrease in viscosity for thixotropic fluids. So in other words, the longer the fluid undergoes a shearing force, the lower its viscosity. For rheopectic fluid, this is a time-dependent increase in viscosity. The longer the fluid undergoes a shearing force, the higher its viscosity. So first, for a thixotropic fluid, it undergoes shear thinning or pseudoplastic behavior followed by a recovery. And here you have a rheopectic or dilatant behavior followed by a recovery. This relates viscosity to shear rate. This is a little clearer, and this shows how viscosity changes with change in shear rate. So for a Newtonian fluid, so here you have viscosity versus shear rate. For Newtonian fluid, no matter how fast you shear it, the viscosity remains the same, or remains a flat line. For shear thinning or pseudoplastic materials, viscosity decreases. So as you increase shear rate, you get a decrease in viscosity along the y-axis. So how fast you mix it determines how thin it becomes. For shear thickening, viscosity increases as shear rate increases, so the faster you shear it, the more viscous it becomes. In a thixotropic material, viscosity decreases as the shear rate increases over time. After a fixed time, it can remove to a more viscous state. For rheopectic fluid, viscosity increases as shear rate increases over time, and these can become nearly solid if you shear them long enough. So, for a solid or a liquid, you need to qualify viscosity and elasticity. You don't really have a true solid or a true liquid when you're dealing with a real material. These display one or both of these properties at the same time. You can get liquid-like properties in a solid or solid-like properties in a liquid. So you really do have to describe which property dominates, elasticity or viscosity. You also have to specify the magnitude of the stress. You have to specify the duration of the stress, whether it's short or long, and what other parameters must be considered, like frequency of the stress. So, given our understanding that we've now kind of gone through, we can now define solids and liquids in the following manner. A solid is a material that will continuously change its shape when subjected to a given stress. For a given stress, there will be a fixed final deformation. This may or may not be instantaneously reached upon the application of stress. A liquid is a material that will continuously change its shape. It will flow when subjected to a given stress. And this is regardless of how small the stress may be. Viscoelasticity is used to describe rheological behavior that falls between a Hookean elastic response and a Newtonian viscous response. So a solid with viscoelasticity is a viscoelastic solid, unsurprisingly. But there are many more ambiguous terms for liquid with viscoelasticity. We're going to refer to a liquid with viscoelasticity as an elastic liquid. Now, oftentimes, non-Newtonian viscoelastic are used interchangeably, and that really should be qualified. Non-Newtonian liquids are ones that cannot be described by the Navier-Stokes equations. These may or may not possess viscoelastic properties. All viscoelastic liquids are non-Newtonian, but not all non-Newtonian liquids are viscoelastic, as indicated by this snazzy Venn diagram right here. So you have a bunch of non-Newtonian liquids, and viscoelastic materials are part